Welcome to This Explainer. Today, we're diving straight into the fascinating, complex engineering behind modern UAV propulsion systems. We constantly marvel at drones for their insane cameras or their autonomous flight paths, but today, we're looking completely under the hood. We're going to uncover how specific missions, whether that means loitering for 16 hours straight or executing a crazy high-G dive, literally dictate the exact right tool for the job.
To make sense of this whole engineering landscape, we'll be breaking things down into 4 distinct architectures today: IC propulsion, pure electric systems, hybrid power, and finally, hydrogen fuel cells.
All right, let's jump right into Section 1, ICE propulsion architecture, or as I like to call it, the brute force. So to start us off, you can really think of internal combustion engines, or ICE, as the heavy lifting marathon runners of the sky. I know batteries get all the hype lately, but ICE systems still absolutely dominate medium to large UAVs simply because of the sheer raw energy density of hydrocarbon fuels. Take a look at this. It's a deconstructed MD-550 four-cylinder two-stroke boxer engine. It's a mechanical work of art designed for heavy 200-kilogram strike drones. Notice how those pistons are laid out flat and directly opposite to each other? By firing in opposite directions, this design naturally cancels out first-order inertial forces. And why does that matter to us? Because it dramatically reduces high-frequency vibrations. That is absolutely crucial if you want to protect the delicate navigation components and sensors on board during a grueling 2,500-kilometer flight.
But depending on what the mission actually demands physically, engineers have to be incredibly picky about their power plants. As we break it down here, they might go with that heavy, 50-horsepower boxer we just talked about. Or if space is at an absolute premium, they'll opt for a Winkle rotary engine. Since it completely eliminates reciprocating parts, you get this incredibly compact, low-vibration profile, which is just perfect for light stealth and recon missions. But what if the goal is to keep a reconnaissance drone circling above a target for well over 16 hours? Well, then they pivot to a hyper-efficient 4-stroke single-cylinder engine, which actually burns about 40% less fuel than a 2-stroke counterpart. It's all about matching the engine to the mission.
And when you look at how these systems scale physically, it's pretty wild. You can clearly see the massive shift from those heavy strategic platforms all the way down to lightweight 15-kilogram tactical units. It's important to note, these smaller systems aren't just, scaled-down versions of the big guys. They face totally different engineering constraints. They need extreme fuel economy, the sheer structural integrity to survive brutal 10G catapult launches, and they need harsh cold start capabilities to fire right up in temperatures plummeting all the way down to minus 30 degrees Celsius.
Moving on to Section 2, Electric Propulsion Systems, the Silent Assassin. Now, this entirely different tactical domain is all about pure electric systems, using brushless DC or permanent magnet synchronous motors. These give you instant torque, extreme maneuverability, and that near-zero acoustic stealth that is absolutely mandatory for highly dynamic, short-range missions. But here's the thing. The real magic in modern electric systems isn't just the motor itself. It's how you control it. The industry has shifted pretty much entirely to FOC, or field-oriented control, which lives inside the electronic speed controller. By running some seriously complex coordinate transformations, FOC perfectly aligns the magnetic fields inside the motor. The result? It completely eliminates what engineers call torque ripple. You get this perfectly smooth sine wave that kills vibrations, slashes acoustic noise, and can actually boost the entire system's efficiency by up to 20%. That's a huge upgrade. Of course, to feed those silent, ultra-responsive motors, you need a serious power source. Modern systems rely on advanced lithium batteries, specifically cutting-edge cylindrical cells like the Molicel P50B 21700 series. These little powerhouses can deliver 60 amps continuously and a staggering 100-amp pulse discharge. To put that into perspective for you, that's enough current to power an entire small house for a brief moment, all coming from a battery pack you can literally hold in your hand. That massive burst of energy, combined with incredibly low internal resistance to keep things from overheating, is exactly what lets a drone pull off those extreme high-G evasive maneuvers at a moment's notice.
Okay, let's explore Section 3, hybrid power propulsion, which is really the brainy compromise here.
Finding that sweet spot between combustion and pure electric power brings us to the decathlete of the sky, the Hybrid Electric Propulsion System, or HEPS. This setup intelligently fuses the long-range endurance of hydrocarbon fuels with the rapid, instant response of electric motors. When you're building one of these, you have to look at the fundamental mechanical differences in the topologies. On the top diagram, series architectures physically decouple the engine from the propeller, so the engine is basically just spinning a generator at its absolute most fuel-efficient RPM, making it fantastic for high-altitude endurance. Now on the bottom, parallel architectures actually use a clutch to allow for direct mechanical drive. That saves weight, lets both the gas and electric engines peak at the exact same time for maximum power, and even lets the drone shut off the gas engine completely to slip into a silent, pure electric stealth mode. But let's be real, having two power sources is completely useless if you don't manage them efficiently. Running these parallel systems requires a highly intelligent digital brain. Engineers are now tapping into model predictive control and dynamic programming. These systems actually look ahead at the drone's flight path to anticipate precise power loads before they even happen. Combine that with multi-factor reinforcement learning, and the drone's AI can dynamically decide, totally on its own, exactly when to burn fuel and when to rely on the battery. It adjusts for things like wind shear, air pressure, and even motor aging on the fly. This level of intelligence alone can save up to 40% in overall fuel consumption. Mind-blowing, right? And that brings us to Section 4, Hydrogen Fuel Cell Propulsion, the absolute future frontier. Finally, we're looking at the absolute cutting edge of UAV engineering, proton exchange membrane fuel cells, or PMFCs for short. This is a revolutionary leap. The goal here is to perfectly blend the incredible endurance of combustion with the zero-emission, silent stealth of an electric drive. When you stack standard lithium batteries up against the high-energy density electrode stacks found in PMFCs, well, the numbers just speak for themselves. Operating on a parallel power control architecture, we are looking at a massive, game-changing jump in capability. We're talking about taking typical electric flight endurance from a mere 40 minutes and stretching it out to well over 12 to 15 hours of continuous flight. And yes, this is a milestone that is already being tested out in grueling, real-world environments. Now, as you might guess, this kind of extreme endurance doesn't exactly come easy. It brings up some genuinely daunting material science challenges. Hydrogen is notoriously tricky to store and handle. To actually make these systems viable at high altitudes, engineers have to develop highly specialized, low permeability materials. These materials have to safely operate and contain liquid hydrogen at plunging temperatures of -70 degrees Celsius, all while somehow not becoming brittle, cracking, or leaking under immense atmospheric pressure. It's a massive engineering hurdle.
Which leaves us with this final kind of wild thought to take away today. As we see all these disparate technologies start to converge, as AI flawlessly manages complex parallel power networks, and as advanced material science slowly unlocks hydrogen's true long-lasting potential, are we finally hitting the physical ceiling of drone endurance, or are we literally just getting started? Thank you so much for exploring the incredible mechanics of the skies with me, and I really hope this explainer gives you a whole new perspective the very next time you see a UAV in flight.